Welcome everyone online. We're really pleased to have Aiden Doherty from Oxford, who's going to tell us about wearables in Biobank and how they can replace questionnaires.
Yes, so I went for a deliberately provocative title, probably just to try and get some extra bums and seats into the room. I don't hate questionnaires, but I'd like to see if there's times that we can replace them. And the other thing you might find a bit amusing is my PhD was originally in computer science, despite me not being so helpful to Lindsay there and trying to get things set up with the title or with the slides beforehand. But a huge thank you for taking time out of your busy schedules to come along. So I lead a group of about 20 people in Oxford who, like myself, are unhealthily obsessed with wearables and their potential application to large-scale biobanks and biomedical studies. And I'm going to share with you over the next 35, 40 minutes or so, then some of the work that we are doing in Oxford, and also sharing bits of work that I get really excited by that take place outside of Oxford as well. And there's a couple of biases that I carry into this talk, so I'll try and be as upfront as I can about those to begin with. The first is I don't believe what people say, as I get to my next slide here, because what people say and what people do as assessed by a device are really quite often very different things. So here's an example then of the Hunt study in Norway, who handed out thigh-worn accelerometers, which are kind of activity trackers that measure your movement, and they're a really good measurement of sitting time. And they looked at then essentially the agreement or maybe lack of agreement between self-reported sitting time, which is on the y-axis, and device-inferred sitting time, which is on the x-axis. And as you can see, this Bland-Altman plot, there are very wide limits of agreement. And additionally, there's not a great correlation between these measurements. Correlation is in a range of around 0.2 or thereabouts. So what people self-report or perceive is quite different to what a device measures. And then to give another example, in the world that Becky would be very much an expert in then on sleep research, this is an example of the UK Biobank. I'll tell you later how the y-axis was derived from the device-measured sleep time. But here in about 66,000 UK Biobank participants, on the x-axis we've got self-reported sleep duration, and the y-axis then we've got device-measured inferences of total sleep time, and these are deciles. So we go over to the very right-hand side, we got a group of about 6,500 Biobank participants that think they sleep 12 hours a night. And then we come over to the left-hand side, we've got a group of about 6,500 participants who think they sleep 3 hours per night. And we look at kind of essentially then whether the median for both of these is on the y-axis, the device thinks these two groups of people are sleeping about maybe 7.5 hours per night. So we get these widely different inferences on what you might think is a relatively simple trait, such as sleep duration. Again, the correlation between these two traits then is around 0.2 or thereabouts between device-inferred sleep duration and self-reported sleep duration. So my bias that I carry into this is it's very hard to self-report our behaviors. So if I can avoid trusting what people say about what they do, I really want to do that. And then the other bias I've got is being in Oxford. This is the most plagiarized slide probably in Oxford Medical Sciences. So it's talking about the power of large numbers. So we're quite simplistic in our thought processes in Oxford. We like big, simple studies. The example here then is my colleague Sarah Lewington then, who's looking at the association between ischemic or systolic blood pressure and ischemic heart disease. If I've got a Framingham size study on the the left-hand side, and I'm trying to look at the association within particular age groups between systolic blood pressure and ischemic heart disease, it's really quite difficult to see signals in a study of 5,000 people. But as I go up to 50,000 people and 500,000 people, you essentially get these engineering scale diagrams as we get much more clarity and seeing that high blood pressure is associated with higher risk of ischemic heart disease, but particularly in the older age groups because there's a y-axis is on the log scale. So that's my other bias, that I like large, simple studies. And my final bias, I believe, then is I love my team in Oxford. So a lot of the examples I'll give through the rest of the talk is from a lot of work that we've done, but there's amazing work done elsewhere in the wearable space as well. And then finally, been inspired by people like Marcus Manatho and others here at Bristol. We love open science. So any of the methods that we derive, we put them on GitHub so that so essentially the clever PhD student in Stanford who will come up with much better ideas than us on how to use the measurements or to improve the measurements can do so. And additionally, any of the measurements we derive, we return back to the biobank resource. So again, that the other people with the more clever ideas than us can build on top of that and make it better. So the resources that we use then are very unashamedly focused on the humble wrist-worn accelerometer. Now, what's a wrist-worn accelerometer? Well, all of us have got an accelerometer in our phones. Essentially, an accelerometer measures how much you're moving. So it measures acceleration forwards and backwards, side to side, up and down, and does so about 100 times a second across these studies. So it means, for example, in the UK Biobank, we have about 180 million data points per participant per week times 100,000 participants. So it offers this opportunity to have an exquisite measurement of a person's movement-related behaviors. And we've got a few studies that have influenced my thinking. So one being the UK Biobank, 100,000 people wore the device for 7 days. China Kadoorie Biobank, we followed the same protocol then to measure it in 20,000 individuals. The English longitudinal study of aging in 4,000 individuals, and the Charles study in China, the Chinese Health and Retirement longitudinal study of aging, had a measurement in about 12,500 individuals. So it's these studies that have influenced my thinking for what I'll talk about through the rest of the rest of the talk. And then if you give a person, well, there's two questions. If I've got a large scale biobank and I'd like to have a wearables assessment, how many people will say yes to wearing the device? And as you can see, there's different numbers across the studies. I guess I'm going to pick the numbers I like best, aren't I? Which is about the 80% range. Why am I not picking 47% as we have in the UK Biobank? Essentially, in the UK Biobank, people were sent a cold email about 5.5 years after they last had been in an assessment centre. And essentially, then they were asked, would you like to take part in a physical activity monitoring study? If so, please reply back and say yes, and we'll send you out a device in the post. With the China Kadoorie Biobank, the ELSA, and the Charles studies, they were collecting other measurements at that time. And essentially, here at the China Kadoorie Biobank, at the end of their visit, they had a pile of devices lying on a desk saying, would you be happy to take one of these for 7 days and then to return it back to us? So there's different modes of asking people. So if we want the pessimistic one, the UK Biobank, 47% consent rate if you've not interacted with people in the cohort for a while. The more optimistic side is about 80% or thereabouts if you've got people engaged as part of other assessments. Then the next question is, if I give a device to someone, will they actually wear it? And it's pretty consistent, as you can see, across the 4 studies, that about 9 in 10 people will wear the device for sufficiently long for us to get a nice, stable measurement of their activity and sleep status. We define that based on having at least 3 days of wear. based on doing missing data simulation analysis in about 30,000 UK Biobank participants. But of course, there are definitely going to be biases as to who agrees to wear a device. So with the UK Biobank, our goal was to have 100,000 participants with device-based data, but we had to send out almost 250,000 email invites for that. And it's really quite interesting looking at those who responded to say, yes, I'm happy to take part in the study versus those who did not respond. So I've got then the x-axis years since they were asked the question, and then the y-axis is the cumulative mortality rate in both groups. So I'm sure you'd all agree with me. If you're ever asked to wear a wearable, you should say yes, definitely. But of course, it's the types of people who say yes then that are as you can see, clearly healthier with a lower cumulative mortality rate. We really try to unpick this apart to see, is there some driving demographics at least, but the odds ratios for everything hover between 0.98 and 1.02. So there's nothing particularly strong, maybe apart from ethnicity. So those from a non-white background had an odds ratio of 0.9 of accepting to be part of the study. But I think there's certainly some residual uncaptured confounders that are explaining, I guess, that we're not capturing, I think, as part of the biobank study, then that are an explanation for why this more healthy group of people are saying yes to this type of questionnaire. And then the beauty of the UK Biobank accelerometry data collection is it's been about almost 10 years now since the participants wore the device. So it's starting to become interesting for a variety of epidemiological studies. And I could pick any one of a number of favorite disease areas. This is one that is a nice exemplar then of what might be the added value of a device-based measurement versus a self-reported measurement. So this is looking at non-alcoholic fatty liver disease after about 8 years of follow-up. So on the left-hand side, we've got the device-based measurement. On its x-axis is median daily step count, y-axis is hazard ratio for non-alcoholic fatty liver disease. And we got the same on the right-hand side, but with the self-reported physical activity questionnaire, we got MET minutes on the x-axis. Now, I guess one interpretation of this is, do we really need to go to all the hassle to send 100,000 people a device by post to find out that higher levels of physical activity are associated with a lower risk of non-alcoholic fatty liver disease? We could have got that in the questionnaire. Fair point, but what's really quite striking here is the magnitude of the association. If we look at the people in the top quarter of the distribution, their hazard ratio is 0.33 versus when using the self-reported questionnaire data, the hazard ratio in the most active group is 0.61. So we're getting approximately a doubling of strength of association that we observe when using the device-based measurement versus the questionnaire-based measurement. And it's actually pretty consistent with other emerging evidence with device-based studies. So this is a really nice paper by Ulf Ekelund and the BMJ from a few years ago that is essentially trying to assimilate most of the accelerometry-based evidence and then also compared to the self-reported evidence, looking at all-cause mortality outcomes. And again, we can see most active group maybe about a 25% lower risk when using self-report versus perhaps about a 50 to 60% lower risk when using the device-based evidence. So of course, I'm quite biased in this, but I think it's a really nice success story from the physical activity epidemiology community that by getting more precise measurements, we can see that we're, I think, finding really exciting new insights then showing that physical activity, at least based on the observational evidence, is probably twice the strength of association from what we previously thought. And of course, the beauty of being linked up to a resource such as the UK Biobank is you can essentially pick your favorite disease outcome of choice. Physical activity is not universally good. So if you're in inguinal hernias or for osteoarthritis, outcomes are carpal tunnel syndrome. Those who've got higher levels of physical activity, observationally at least, appear to have a higher risk for those outcomes. But then, obviously, as expected, the balance of the rest of the disease areas, higher levels of activity, are usually associated with lower risk of diagnosis of various disease outcomes, particularly strong associations for example, type 2 diabetes and various circulatory diseases as well. And sorry, the x-axis was per standard deviation higher of accelerometer measured physical activity levels. And this was work carried out by Ellie Watts at the National Cancer Institute in the US. But as I've said, an accelerometer can measure how quickly a person's going forwards and backwards, side to side, up and down, does so 100 times a second. So basically, all these studies are doing is taking 180 million data points and getting essentially a glorified average from that. Person does lots of activity versus person doesn't do very much activity. And we can get really far with that. But there are more sophisticated signals that one can derive from that. One of my favorite examples to show is by researchers at the University of Sydney then, who are interested in this concept of vigorous intermittent lifestyle physical activity. What do I mean by that? It doesn't exactly roll off the tip of the tongue. It's this concept that quite often people ask me not how much exercise do I need to do, Aiden, but it's more so how little exercise can I get away with. So what they've looked at is people in the UK Biobank who report doing essentially no structured physical activity or exercise. That's a group of about 25,000 individuals. And they said, but there's still an opportunity to get in some short bursts of activity, such as, I don't know, imagine you're getting the tube in London and you've come off the train and then you've got the automated escalator going up. You can either stand on the escalator or you might try and be good and walk up the steps and then maybe 3/4 of the way up regret that decision because it's getting tougher and tougher going up. So you're getting a short burst of vigorous activity there. Or imagine the bus is just about to take off at the bus stop. You're about 100 yards away and then you might run then for that bus. So there's opportunities to incorporate some short vigorous bursts. And in their analysis, the results are almost miraculous. So in the x-axis, they've got how many 1 minute bursts of activity you can integrate into a day. And the y-axis is hazard ratio for premature or all-cause mortality. And if we look at the group of people who can incorporate 3 minutes of these bursts of activity into their day, there's apparently a 25% lower risk of all-cause mortality over a 7-year follow-up period. They've tried to do lots of different sensitivity analysis to explain this away. There must be some residual confounding because as the group of people who do 0 minutes, it might be this. It's not because they're so lazy they can't be bothered to do it, but it might be just they can't incorporate these short bursts. So I'd really love to see this replicated elsewhere. But I guess so tantalizing is the hypothesis that if I could just do a couple of minutes of intense exercise a day and would get maybe a 25% lower mortality risk, it's a very tantalizing prospect. So hence it generated loads of media interest, this particular study. And it's also likely, of course, that because we've just got a 7-day measurement on individuals, that we may well be underestimating the strength of association for physical activity with disease outcomes via regression dilution bias, which and obviously we're a huge fan of a paper that Louise Millard from here then put out a year or two ago, looking across all the variables in the UK Biobank to see how strong is their repeated measurement component of that. So inspired by that, we looked at the accelerometry data, whereby we set up a study in the UK Biobank to re-invite 3,000 people to wear the device again and again and again and again. So they had 4 repeated measurements about 3 to 4 years after the original 7-day measurement. And you can see the intra-class correlation coefficients hover between 0.7 and 0.8 or thereabouts. So showing actually this is a nice, stable, repeatable measurement. It's kind of on a par with blood pressure or thereabouts in terms of its repeated measurement ability, which actually we're quite pleasantly surprised with, because we get all these anecdotes of, oh, this wasn't a good 7 days for me. I didn't do my usual level of exercise, but we're seeing it actually as quite a highly stable trait. And then an exemplar analysis then showing, for example, if you're interested in coronary heart disease outcomes, looking at a standard deviation higher or thereabouts of step count. The uncorrected measurement hazard ratio is apparently 0.87. Then we correct for the regression dilution coefficients. The hazard ratios might be closer to 0.8 than 0.87. So, and again, this is an exemplar analysis looking at just coronary heart disease. But to me, at least, it's very promising that we've got strong repeated within-person correlations on these. And then, oh, sorry. Hmm.
They
Or
are actually having less, that they are actually having more or less steps, like it's not a measurement error.
Mhm.
There's variation in.
It's variation, I guess. So this week, or I guess, well, first of all, from this week to next week, I'm not going to do the exact same number of steps. So there's obviously some uh, uh, variation in the behavior itself. Is there variation in how we interpret step counts based on a different? So is there a measurement error in that? Yes, absolutely. The measurement is not perfect. It's an inference of a signal. So there's probably a combination of the behavioral variation and the measurement error of the inference of the steps from the device-based signal. So it's, I guess, trying to capture some of that. And then, of course, with the measurement being 3 to 4 years later, there might be some elements of a decline of trajectory, but that should be roughly similar between both groups with respect to what analysis you're doing as well. So it's hard to pinpoint the exact reason for that. But what we're quite pleased about is that it's a pretty high repeated ICC values that we're seeing from that. Yeah, thank you. And then we're getting into what I get most excited about most mornings then as well. Is there some extra signal we could squeeze out of this information? Because the intuition is, well, I'm getting these 100 measurements a second and 3 axes. Surely there's going to be some pattern or signature that's unique to when a person is sitting versus when they're walking versus when they're driving or doing other types of activity behaviors. And in the past, there have been a couple of major limitations, the reliance on small sample sizes and validation studies. Another challenge is how do we have a ground truth or a reference measurement to know what type of activity a person is doing? And then finally, it was just the computational methods we were doing could have been better. So first of all, in terms of having a reference measurement, a a tool that quite a few people are now getting used to using is wearable cameras. So essentially, these are cameras, a bit like a GoPro camera that you wear on your chest, and it takes these first-person point of view images. And generally, from the camera images, it's bleeding obvious what a person is doing. So we can see when they're sitting, when they're running, or when they're rowing in this case. And then what we do is give them the accelerometer that's used in our larger cohort study to wear on the wrist as per usual. And then we can essentially time align both signals. So for every 30 seconds, then we have essentially a reference measurement for the type of activity behavior a person is doing in free living environments. And then it becomes essentially a sandpit for a machine learning or a data scientist to try around their favorite time series machine learning methods to try and measure these human activity behaviors. And the way we'd have done that in the past is, and I'm going to awkwardly work from the bottom to the top of this slide. So we would have our raw sensor data, we'd take our 30-second window of the data, And you just pick out your favorite time frequency domain features. I might take the mean of the signal, the median of the signal, the interquartile range, the Fourier transform coefficients, etc. Then I would plug them into my favorite classifier of interest. Our favorite at the time was random forests that work that are hard to explain but work frustratingly well across a range of different tasks. So we put it into a random forest classifier that would then say for every 30 seconds what type of activity a person is likely to be doing. And then finally, we'd apply a time smoothing technique over that, such as a hidden Markov model. The intuition being that if I'm for every 30 seconds sleeping, bike riding, sleeping, it's unlikely I went for a 30-second bike ride in the middle of the night, so it smooths over the erroneous classification then. So these hidden Markov models or LSTM models work beautifully on time series data. But a guessing point we're always making is this point here. How do I extract out some relevant features to capture a unique signature in this data? I'm making a guess if I'm taking a time or a frequency domain feature. I'm just using what everyone else has used without thinking. So we're really excited by a technique called self-supervised learning. You could maybe affectionately think of it as ChatGPT for wearables. Because the intuition is our labeled data sets are generally quite small, but there's huge unlabeled data sets. So the UK Biobank, we didn't put cameras in everyone, but everyone has worn a device for 7 days. And the intuition is I can create some simple proxy tasks for a machine learning network to try and accomplish. And then in trying to accomplish that, it's got to try and figure out how to self-learn some features that are really fundamental to human motion dynamics. So to give an intuition for a 10-second signal in the UK Biobank, I can create some deliberate perturbations to that signal. I can reverse it around. I can stretch it out by time warping it, or I can add some permutations to it. So then I essentially train a humongous neural network then to see for every 10 seconds, can it pull out some features that helps it identify whether a person's going, whether the signal's in its normal time form or in a reverse time form, permuted time form, or a time warped time form. I can do this across 7 billion training samples in the UK Biobank. And does it work? Well, sorry, then how would we do it? And you train your big huge neural network, and then you can essentially say all these early 40, 50 layers are trying to extract some features in the data. And then what I'll do is just my final layer, I'll just replace it and fine tune it for whatever task of interest I have. So it could be replaced for a task to identify as a person walking, running, sitting. It could be replaced if I got a separate task then for example, sleep polysomnography data, are they in REM sleep, non-REM sleep, awake? Or I can retrain the final step for are they stepping or not stepping, or how many steps are they doing versus not doing. So it's a really flexible framework to pull out features from the time series data on the accelerometer. And of course, there are huge interest in the field, so there are other alternative approaches. So what we've done is essentially this augmentation recognition method, but there are others in terms of trying to reconstruct the signal, whereby you hide bits of signal and then see if you can reconstruct or guess what happens next. And there are joint embedding approaches via approaches called contrastive learning. So there are other alternative approaches out there. Being in Oxford, we just liked big and simple, so we just trained it on the whole UK Biobank using the most simple augmentation recognition method.
Are those features
Um,
the feature there is continuous, or are you learning to?
it's categorical that we're learning at the minute, yeah. So it's just which one of the 4 forms is it? The kind of the normal time form, the reverse, the permuted, or the time warped? Yeah. So it's so very simple with a categorical outcome. Yeah. Does it work? So there are a range of data sets out there that are human activity recognition data sets. So essentially they've had either a camera ground truth or they've had For example, I might follow Becky around with a clipboard and then write down what activity she's doing. So there's a variety of ways of capturing it, but these are open data sets. So does the self-supervised learning work? Yes, it definitely does give a nice improvement, and particularly for tasks in which there are smaller amounts of data available, it helps you get up to a good level really quite quickly. So we now use it across everything we use. We use the self-supervised learning as our head start then to extract better features. And of course, a question might be, well, how well is this going to work in maybe my disease specific subpopulation of interest? Will it work or not work? So some things give me hope. One is for people with Parkinson's disease, doing a human activity recognition. It was incredibly helpful and dramatically improving the performance of what we could do before to identify activities of daily living. And then one of my favorite papers came out about 5 weeks ago or so from a group of researchers in Berkeley that work with a project called the Earth Species Project. So they actually put accelerometers on different animals. So here's one where they've put on a polar bear. So the polar bear's got accelerometers on it, and it's got a camera underneath its neck, so that helps give them their ground truth for the type of activities that the polar bear is doing. And they don't just look at polar bears alone, they also have got accelerometer data on snakes, whales, turtles, etc. And in the past, what they would do, for example, in the bottom right here, I'd have my polar bear classifier. So I'd train on data just the polar bear alone, and then try my best to identify, is it head shaking or rolling or grooming or walking? And my F1 classification score then would be about 0.23 or thereabouts. What they then did was they took the model that was trained in the UK Biobank, so in humans, to give a heads up on the types of features to try and identify them. And then they retrained the final layer on the polar bear alone, and then F1 score goes up from 0.23 to 0.68. And you can see across 9 species that the general F1 score went up from 0.5 to 0.8 or thereabouts when you give it a heads up from the human pre-trained data. So it makes us again quite confident that probably our classifier, if it can help generalize to polar bears, it might help generalize to other humans as well. So this is one of my favorite papers recently. So what can we use it for? So we've got our self-supervised learning that can now identify uh, 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 time spent in, for example, different activities as to how much time UK Biobank participants can make an inference now. They spend asleep in light activity and sedentary behavior and in moderate to vigorous physical activity time. So then we can use different methods then to look at perhaps how, if I reallocate time from light intensity activity to moderate intensity physical activity, might there be some consequences then for subsequent disease outcomes or not? We might naively like to apply a linear approach to this, but if I use, I don't know, for example, a Cox or logistic regression, and I say I do an extra hour of moderate to vigorous physical activity, I assume I hold everything else constant. But then I've broken the assumption that there's a 24-hour day. So I can't make a 25-hour day. So hence we're quite interested in approaches called compositional data analysis approaches that look at the ratio of time between different activity behaviors that respect the constraint of a 24-hour day. And we get, for example, here on the left-hand side, we're then looking at reallocating time, almost trading time off between light intensity physical activity and moderate to vigorous intensity physical activity time, while holding sedentary behavior and sleep time constant. And we can see then on the y-axis and the estimated hazard ratio, there's a stonking great association as more time is reallocated to moderate intensity physical activity behaviors from light intensity physical activity behaviors for cardiovascular disease outcomes. But then for cancer, we see quite a different story, whereby there doesn't seem to be any apparent helpful association in reallocating more time to moderate intensity physical activity behaviors from light intensity activity behaviors. So essentially, one interpretation of this might be for cancer. It appears that just pottering around, being active is helpful, but you need not necessarily do really vigorous, intense behavior. So there doesn't seem to be a particular benefit for that with respect to cancer outcomes from this observational data. What else can we do then with, we've got self-supervised learning, what other types of phenotypes can we extract out from the biobank resource or any resource that's got accelerometer measurements? So approach where a measurement that I love is step count, because in the past all the research studies essentially had this measurement called milligravity units, which is in terms of physics, it's a beautiful measurement, but in terms of interpretation, it's a horrible measurement. Step count, everyone understands that. It's actually quite difficult to measure because the device is on my wrist, but the stepping is happening down at my ankles, and it's not a straightforward task to do. And you see previous steps in the field got really wide limits of agreement as to what a device thinks a person is stepping versus what a camera ground truth says they're stepping. But then using the self-supervised learning, we essentially regularize it a bit to then see for every 10 seconds, is a person likely to be walking or not? And that's to try and filter out episodes of, for example, a person's brushing their teeth, which would give you a really high step count if you had a naive peak-to-peak detection algorithm. But instead, we filter out those and just concentrate on the episodes where we think walking is happening, and we count these peak-to-peaks to give you a reasonably good inference then on what your step count is. You can see a nice tight Bland-Altman limits of agreement on the right-hand side. And then what type of analyses then might one be interested in using the step count? You can pick it as an exposure, an outcome, a covariate for any type of analysis. This is one I was quite interested that an MSc student did at Oxford last year, then looking at gene by environment interaction analysis with respect to cardiovascular disease. We're still scratching our head around this one a little bit. If I squinted it enough, well, first of all, there are confidence intervals that might be overlapping a bit, but I might say maybe there's a trend for the people who've got pre-existing high and moderate genetic risk for cardiovascular disease, that step count perhaps might be helpful, but then perhaps for those who've got a pre-existing low polygenic risk score for coronary heart disease, step count doesn't really seem to make any difference, or for people who step more versus step less. We're currently scratching our head around this one, but at least have shared a preprint, so I'm sure people more clever than us will come up with a better interpretation of this data. And then, of course, the measurements, we can also make inferences. I would say inference, they're better than guesses. They're inferences, but they're not perfect inferences of time spent in sleep behaviors. So in the past, lots of the sleep inferences have been validated on pathetically small polysomnography validation data sets of maybe about 20, 30 individuals. The largest was 100 individuals. So this is a picture of Hang Yuan, who's an early career fellow, then the group who works closely with Becky there too. And what Hang did was simulated different polysomnography data sets, totaling about 1,500 people who had an overnight polysomnography assessment with a concurrent wrist-worn accelerometry assessment. We've used the self-supervised learning then plugged into a recurrent neural network to try and identify time spent, whether a person's awake and as to what type of sleep stage they're in. We then discovered it was too tricky to say whether they're in very deep sleep versus somewhat deep sleep versus less deep sleep. So we cheated then and just combined those together and just said it's non-REM sleep. So we had three simple classes then of REM versus non-REM versus wake. And again, you can see that the SSL, self-supervised learning approach, helps us do better, but not maybe wonderfully, excitingly well. So because we got wake versus REM versus non-REM, a kappa score of 0.37. I wouldn't bet my house on this as an outcome measurement in a randomized control trial. And I think we really need signals beyond the accelerometer itself. So we need some physiological signals to go along with that. But what we can do reasonably well is to tell whether a person's asleep versus awake, and also what their sleep efficiency score is like. And again, there can be a range of different analyses one might wish to run on this data. One, for example, then might be looking at possibly what might be the genetic architecture of sleep architecture. So this is work that we'll soon put up on a preprint, then looking at a GWAS against these device measured traits for nighttime sleep, sleep efficiency, REM sleep, and non-REM sleep. And there's a particularly interesting locus in chromosome 2 then that there appears to be uh, if the alleles are in a particular way, then that you get 8 minutes extra of REM sleep at the expense of non-REM sleep, and that kind of switches over the other way around then for people who are not like that. As to how important that is or not, we're still scratching our heads around that one as well. And then what else could I use a device for in my last few minutes? I'm also really interested in identifying disease-specific signatures. So in the past, I talked about extracting features to know a person is walking or bike riding or swimming, which is helpful for subsequent epi tasks. But can I just see within when a person's walking, might they be exhibiting some gait-related disorder that I could pick up there and then within the signals? The idea here is that I look at maybe just my light and moderate to vigorous physical activity time when I'm walking, and then might there be some signature within that walking that indicates whether I've got maybe diagnosed Parkinson's disease, prodromal Parkinson's disease, or whether I've got some healthy-like score, and I could sum all that up, and then I would say maybe this particular person is most likely to be exhibiting gait-like or Parkinson's disease gait-like symptoms. Is that useful or not? So this is work done by Aiden looking at risk prediction for Parkinson's disease in the UK Biobank. So I've got my baseline, kind of your usual demographic factors. To start with, if I had an apologenic risk score, it might give me a little bit extra of a boost in my C index. That's usually always very hard to shift. Then perhaps I could add an overall activity, which is kind of simple measurement in the accelerometer. And then finally, what seems to give a nice boost is if I trained on a separate data set a model to identify within just the walking episodes the person is likely to have belong to the Parkinson's disease group versus the healthy control group, then apply that in biobank participants who do not have any prior diagnoses. It does seem to give a nice shift up in the C index and being able to predict Parkinson's disease diagnosis 8 years later. So this is one that we're writing up and will soon submit, but it might be a really nice model for looking at other disease areas in which we believe there might be a movement-related signature. So I think this could be a really exciting approach for future. And then just a few final thoughts. Where are we going next? So in the UK Biobank, we're also collecting chest-worn cardiac monitor data. So it records ECG measurements 250 times a second, accelerometry measurements 25 times a second. It's worn by a chest-worn patch. What sort of new avenues could this open up? It can help us do better activity and sleep assessment. But also, of course, we can look at your favorite cardiac arrhythmia of interest as well. One possible example is work led by Stefan van Jouwenboven, who's looked at the exercise bike test data in the UK Biobank, which was kind of a 7-minute sub-maximal exercise test. And he was interested in this concept then of premature ventricular contractions, or I affectionately think of them as skipped heartbeats. And essentially, he looked at in the recovery period after exercise, people who have more of these premature ventricular contractions. We've always thought clinically that it was something benign, but his analysis then of about 70,000 biobank participants was suggestive of a higher risk. So people who got more of these PVCs in the recovery period after exercise do seem to have a higher risk for both cardiovascular and all-cause mortality. Again, it would need to be replicated in another data set, but this is the type of analysis, and it could be also opened up by the because, as I said, this was just a 6-minute sub-maximal exercise test. If we get a 14-day assessment of people in their free living environment, I think we can get much more rich exposure measurements on that. And just to go through the last couple of slides, smartphones are on the menu maybe for future activity assessments. There's a really neat study in Israel, the Khalid cohort, whereby they have 900,000 people who have donated smartphone daily step count data and linked it back up with their electronic healthcare record system and the Khalid healthcare system in Israel. And so there's bound to be some useful signal, but there's also going to be lots of quirks in this data. So, for example, here we can see that men are quite a lot more active than women as assessed with smartphone step counter. But I don't think that's because men are more active than women. It's just men usually wear their phone in the pocket, which is a great place to pick up step counts. But still, there's bound to be, I think, some useful signal that can be picked up from this in future. Commercial wearables are, of course, really exciting. Lots of people now are walking around as day-to-day active users of Fitbit or Apple Watch. I'm really excited by the All of Us cohort study in the US. They've got now Fitbit data on 60,000 individuals and a median wear time per person of 2 years of data per person. And this is minute by minute data over 2 years. Some participants have got up to 10 years of wear per participant. So I think this is actually a transformational leap forward of what we have in the UK Biobank. We just got a 7-day assessment. So I'm really excited by the All of Us cohort and the opportunities that will be offered by that to look at trajectories of activity, etc. And then with the UK Biobank, where are we going next? There are plans afoot for a new cohort-wide repeat measurement or assessment. And very much in the agenda for that are what wearables, maybe nearables or apps could we include in the repeat assessment in the UK Biobank. We're really open to ideas on that. So I lead a remote monitoring working group within that. So we're looking at certainly at the smartphone as a platform. There's a brain health sub-study that we're putting sleep mats in people's homes on, and very much hoping to work with some commercial providers to get more long-term assessments of activity and sleep related behaviors via wearables. But we're really open to ideas on how we can enhance the cohort and make it more valuable for the worldwide research community. And my final 2 slides are the all of this, of course, is showing high income country setting data, mostly maybe apart from the Chinese data, but there's huge, essentially black holes in the world that are not where we do not have wearable assessments. I would personally love to see more LMIC biobanks integrate these wearable assessments, because, for example, with the one of the classifiers we trained, we thought worked beautifully to identify moderate to vigorous physical activity time. We then tested it in a validation data set in China and discovered that it worked pathetically. And I think it's because the classifier lazily learned that moderate to vigorous physical activity is walking and cycling alone, nothing else. Whereas in the Chinese validation data set, we had people doing manual labor in farms, etc., and it just had completely missed that. So we need more diverse biobanks, but also more diverse validation data sets as well. So with that, I'll stop, and I hope that I've well, shared my enthusiasm for wearables as a really great way to enhance cohorts for a wide range of exposures. But B, if we could do this at scale across a variety of studies, I believe it will really help us answer this wide variety of important questions. And if you are excited by that, there's a short course that we're running in Oxford in September for anyone that really does like getting down into Jupyter notebooks and extracting features and time series data, etc. So there's lots of hands-on learning to be done in that. So you or a colleague are interested in that, yeah, please do consider it. And with that, I'll stop. And thank you so much for your attention.
I'm really pleased that I wore my wearable biosensor sort of 2% reduction in mortality.
Oh, yeah.
I'm going for my 5-hour assessment tomorrow.
Oh, wow.
5-hour assessment. And I'm going to say yes to everything. And I'm really pleased that the bike thing is sub massive, so I'm not going to just about do it. Questions? We've got very short.
Oh, sorry, I went on.
Questions for Aiden?
That was really interesting. Thanks so much. I wonder if in the work you're doing, you start to think explicitly about some of the digital inclusion, digital exclusion type factors. And use of wearables.
Great question. I don't think we have thought about it probably as deeply as we should have. So first of all, of course, there's all the usual biases with the UK Biobank, and then within that, it's an even more biased subsample that agrees to wear a device. And I guess our way of getting around that in some ways is going off to work with other cohorts where there are really different sets of confounders, such as the China Kadoorie Biobank, and we've got pilot studies about to run in the Indian study that I know you and Sarah Lewington are working with, and also in South Africa with the Agincourt cohort. But in terms of maybe directly working on digital inclusion, say, for example, within a UK context, I think other people do much better work than us in that.
There's a sort of related question. So you mentioned that the devices weren't good at picking up, say, farm labour and things like that. What about people in the UK that are doing manual work? Could that be picked up if they were participants in Biobank?
I don't know right now, but we're working with collaborators in Denmark who are interested in kind of the physical activity paradox, and then to try and see if we can identify manual work better from the data. So I might have a better answer for you at the end of this year on that. And what it will really need then is good quality validation data sets. So we've got some confidence in the inferences we're making from, for example, sensor signals then as to whether we can confidently say that this might be a person that's doing manual activity X versus manual activity Y versus maybe an office-bound job. Thanks.
You sort of alluded to this, but I think you said you can tell people who are cycling, say. Can you pick out people who are highly active but not stepping? I'm just in bone health, so I'm trying to work out whether from your data you can pull out people who are weight bearing but are highly active.
Great question. I don't know. I'd optimistically, yes. I'd optimistically think there would be a good chance of that. Anecdotally, for example, there's the NHANES data set in the US has got accelerometer measurements in about 10,000 individuals thereabouts. And we can quite clearly see people who are not stepping, are, for example, wheelchair bound or got some severe physical disabilities at that time. So we feel that the step counting method works quite well. Then do we pick up? Yeah, I guess we can pick up biking or other activities, and I guess it depends what the interesting other activity is. So I think you can do it, but nobody has done it yet.
Are there any links between the apps in Israel and the UK Biobank self-supervised?
So are there any links between the the app that was used in the Israel study? So we had the Clalit cohort people come and present to the UK Biobank team. We probably might not use the same app because there's lots of different apps that one can use. There's the radar base platform that's used in quite a few UK studies. There's a care evolution platform that's used by the All of Us cohort and other American cohorts, such as Framingham study. So I think for the UK Biobank, there would probably need to be a tender process then to try and say which app platform might be the one to use. But at the minute, we're just trying to figure out what are the traits that we would like to measure on an app, and then to kind of put that out as part of the tender package. Don't think I fully answered your question, though. If I,
I'm interested if there's a way to harmonize the
harmonize the apps. Good question. So I think with passive measurements, there's always a chance that we can harmonize things because we can have independent validation studies whereby you could use, I don't know, the Clinique app step counter versus, I don't know, the Fitbit step counter versus the research grade step counter and algorithms that one wouldn't fare from research grade devices. With, I guess, questionnaires, it's a bit harder, I think, to harmonize because I can't even go to an independent sample because then I don't know if people in Israel might interpret questions differently to people in South Africa, to people. So again, my simple brain, and I just like to work with passive measurements where I don't need to ask people questions. But there's, of course, a bias I have in that.
Thanks.
Activity during pregnancy or
there's not been a huge amount of work on that. I would love to work on it because I got skin in the game because my wife is a perinatal epidemiologist as well, but we've maybe not been proactive enough and see if we could do a project together on that. But again, you would think that'd be beautifully set up for kind of Fitbit type measurements to get measurements throughout all the trimesters. And then what we really need, I think, in the UK is to be able then to link these measurements back into the NHS digital systems. So again, I think that would be a great idea. Just nobody's done it, and particularly nobody's done it well at scale.
yeah. I might get in touch with you.
Please do. Yeah, please do. Yes, no, really
Don't
very
worry,
good
Aiden,
operation.
yeah, if you email Lucy, Julia, with Lucy, she'll fix you in those 15 minutes.
I'd love to talk more about that. Yes.
Advice to make sure you get your 15 minutes. Okay, I think that's great. So yeah, so just email there's a couple of 15-minute slots
Yeah,
left.
I'm around for the rest of today. So yes.
And also Aiden's email address.
Yeah,
I'm sure you answer emails really efficiently. So that's fine.
I don't mind being live. Yes.
It's really interesting.
Oh, well, thank you very much for coming along.
It reflects what we saw with the MR in that we saw that there wasn't an association with average activity, but not with moderate activity.
Okay.
Yeah.
Oh, that's interesting.
So, yeah, it's really yeah.
Yeah, you forwarded the deal today. That's actually super interesting.
Yes, yeah. Obviously, they're not completely independent studies, because although we used the quantitative consulting data as the outcome, we obviously used UK Biobank.
Oh, yeah.
Yeah, I don't know what it means, but it's interesting, isn't it?
Yeah.
I think it's an older one, really knowledge and not the instruments are not very good, which, yeah.